Hi everyone, I'm Linchao Zhu. I am now presenting more details of our paper, ActBERT, Learning Global Local Video Text Representations. ActBERT is introduced to learn from video text pairs in a self-supervised way. The existing models usually take linguistic features and frame level or clip level features for video text joint modeling. In ActBERT, we leverage three sources of information for cross-model pre-training, which are action-related features, region features, and the language embeddings. For example, visual features of shrimp balls are helpful to predict the token shrimp ball when it is masked out. I will now introduce a new transformer structure for the encoding of three sources of information. The standard transformers usually take all inputs, no matter what modality the feature is. They treat the visual and the text features equally. We introduce entangled transformer to encode each modality. The transformer weights are not shared. To further introduce more interactions between different modalities, we leverage two multi-head attention blocks among the transformers. The global action inputs are used as query to attend linguistic inputs. The output will be combined with region inputs. The combined feature will be forwarded to the region transformer. Similarly, the global action will also attend region inputs. The output are combined with linguistic input, and they will be forwarded to the word transformer. In this way, our entangled transformer utilizes a global queue to guide the selection of local hints from linguistic and visual features. Equipped with entangled transformer, I will now introduce the details of ActBERT training. Here are two clips. The first clip is with description rotate shrimp balls. The second clip is with the description add spinach. The stacked frames will be forwarded to a 3D ConvNet. The action features can then be obtained. The 3D ConvNet is pre-trained with the verb as the label, so the obtained features are action-related. Region features are extracted by a pre-trained object detection model. The action features and the region features are served as visual embedding. We introduce two tokens for each of the features. The act token represents that the input is about an action. The region token represents that the input is local region. There are also word tokens. For those word tokens, their visual embeddings are empty. The segment embedding is introduced to distinguish the two segments. For example, there are two segments, and S sub A and S sub B are introduced. The position embedding is introduced to record the order of the inputs. We have introduced all the input modules, and now we introduce four tasks for ActBERT training. The first is masked language modeling. Similar to BERT training, the word shrimp is masked out. The goal is to predict the masked word shrimp. The second task is masked action classification. For example, the rotate clip is masked out. The ActBERT is trained to predict the masked action. The third task is masked object classification. For example, the region of spinach is masked out. The ActBERT is trained to generate the masked non-prediction. The final task is CrossModel Matching. This task checks if the visual and the text descriptions are matched. We pre-trained our model on how to 100 million with over 100 million video clips. Once pre-trained, we evaluate the pre-trained model on 5 downstream tasks. We evaluate video captioning on uCook2. We outperform VideoBERT by 1.7 on media score. Action segmentation is to assign a label at the frame level. We evaluate on the coin dataset, and ActBERT outperformed the state-of-the-art by 22%. It shows that the pre-trained model can deal with visual inputs where linguistic descriptions are absent. The results on 5 downstream tasks demonstrate the effectiveness of our model. More results can be found in our paper. Thank you.